Let's start. Okay, first question. Considering the following executable to main memory with offset 030, executing on a 32-bit system. Okay. If not provided, assume each data memory location has value 2, and general purpose registers have value 1. So it's 32 divided by 8, which equals 4. All memory locations have a default value of 2, and all registers have a default value of 1. So 0030 plus 4 is 0034, 0038, 0042, and 0046. And then the program counter goes one more at the end of the fetch instruction, or fetch stage. Do it. Okay. So this is L-type instruction. Oh my god, L-type. This is an R-type, another R-type, another R-type, and this is a branch. Okay. Provide value of MAR at the end of the mem stage. For instruction 1. Okay, so L-type has all the 5 stages: fetch, decode, exec, mem, and write back. So at the end of this stage, nothing changes from the exec stage, so it still should have the address where we need to put the data in, which is 30. So this should just be 30. Provide value of MAR at the end of decode stage for instruction 1. Well, the PC is at 30. So during decode stage, it reads from the IR, and the IR will also have 30 for the current instruction. Provide value of C after decode stage for instruction 4. 1, 2, 3, 4. This one. Okay, so at this line, R3 had a 100. Actually, it was after the decode stage, right? Well, the decode stage, nothing has happened yet. So it's whatever was in the Z register from this previous instruction. So that's R2 plus R2. Well, we loaded whatever was in this address. He didn't provide it for us. So a default of 2. So it was 2 plus 2, which is 4. So there should be 4 here. Right? Oh no. This was the decode stage, isn't it? Instruction 4, 1, 2, 3, 4. So this is an R type. So there's fetch, decode, exec, and write back, I think, right? Is that true? I don't even know if that's true. Yeah, fetch decode exit right back. Okay. Well, decode is just for the instruction itself. Um, oh, I'm confusing myself. The reason I needed to know is because I need to know what was in the Z register for this instruction because it doesn't change yet at decode stage. So this is for you. Okay.
Sorry, could you explain
Why
why
it's
is it?
yeah. So this is asking what's in the Z register. That's like the output of the ALU um, after the decode stage for instruction 4. But at the decode stage, you've only decoded the instruction, so you haven't really touched the Z register yet. This is the fourth line of code, right? R3 minus 25. So you don't really care about what's in the Z register after this instruction. You care about what was in the Z register in the line before, and there was an R type instruction, so it put R2 plus R2 in the ALU, and then it was outputted into the Z register.
Oh, okay, I got it. Thank you.
Yeah, and then R2 just has a default value of 2 because he just told us and he didn't specify like that specific address or anything. So it's 2 plus 2, which is 4. Provide value of PC before exec stage for instruction 5 for the last iteration of the loop. Provide value of PC for instruction 5. 1, 2, 3, 4, 5. That's the last line. Um, there's going to be 0050 because when this is finally 0 and 0, they will be equal, so the PC won't get touched, and the PC has 50 after because after the fetch stage, it always moves the PC counter, it increments the PC counter. Provide count of total executed instructions. Let's see. This happens
It
once.
says 00.
Hmm?
It says
Uh,
0048.
48. Did I do the math wrong then?
Yeah, for the answer key.
48. There's no shot it could be 48 though. Oh, um, did I do the math wrong? He did the math wrong because 42 plus 4 should be 46, and then this should be 50. His math is wrong because you always increment by 4, right? So yeah, the real answer should be 50.
Okay, thank you.
Mhm. Provide count of total executed instructions. So this happens once. This happens once. This part here will loop. Let's see. This one we don't really care about. Doesn't really affect us. But when we do this branch, we have to compare R3 and 0. So when it's 100, it'll run once. And then 75, 50. Actually, when it's 100, it'll automatically decrease every. Alright, so there's once for 75, 50, 25, and 0. So it's 4 times. So 4, 4, that's 14 times because it's 12 plus 1 and 1. Provide value of MDR at the end of decode stage for instruction 3 for the first iteration. Instruction 3 is this R4. Yes, 2 plus 2. MDR. Well, the MDR was last touched at the first line of code because we didn't go to main memory for this line of code. So it should still be 2, I think, because we brought 2 for when we loaded that. Is that right? Oh, I messed up. Add the value of MDR at the end of decode stage. Oh, shoot. I forgot. If it's the decode stage, it's still the instruction part. Okay. So this will actually have the instruction itself. The instruction. What did he write? Yeah, MDR contain the instruction itself. Okay. This is fine. Question. I don't think he gave the answer for this one yet. Oh no, he did. Okay. Um, okay. Uh, does it matter that it's a risk processor? I don't think so, right? If not provided, assume each data memory location has a value of 4, and every general purpose register has 2. Okay. Um, we don't know what's in register 1, so we assume that this is a 2. So this is actually the equivalent of 2. So load a memory address 2 into R2. We don't know what's in memory address 2, so we assume 4. So this is actually R2 will have and the second line R2 plus 2, so R2 will then equal 6. And then R3 will have a 4 because when at address 5, and that'll have a value of 4 by default. Um, and R4 is going to get whatever's at this. So this is the same as address 6. We don't know what's in address 6, so default to 4. Um, this is an S-type instruction, so R3 4 at memory address 4, the value in R4. So memory address 4 has a 4 in it. R6, same thing, 4, R1 is equal to R4 plus R2. So R4 has 4, R2 has 6, so 6 plus 4 is 10. We jump immediately to next. So these lines of code won't be executed. Um, jump, and then at memory address 7, we have the value of R4, which is 4. And then in register 4, we put whatever's in register 7. So we don't have that, so go to address 2. Do we have, no, it's an address 2, no. 2 equals 4. I think I did that right. Okay. For the above execution, calculate total data memory access count. So these lines of code won't run. Data memory. So anytime we have to go to main memory. So once, twice, 3, 4, 5, 6, 7 times. For the above execution, calculate the total execution time. Each stage. Okay. Um, I think you can just literally write out the things. So for L type, it's all of them. 5, 25 plus 5 plus 10 plus 20 plus 2. It's an R type. So for L type, it's all of them. Fetch, decode, exec, mem, write back. For R type, it's fetch, decode, exec, write back. For S type, fetch, decode, exec, then mem. Um, and for jump, it's only fetch and decode. So this one is an R type, so 25 plus decode is 5, exec is 10, and write back is 2. This one is still L type, so 25 plus 5 plus 10 plus 20 plus 2, same thing. 25 plus 5 plus 10 plus 20 plus 2. This is an S type, so 25 plus decode 5 plus exec 10 plus mem 20. Sorry, my handwriting's bad. Um, another one of these S types, 25 plus 5 plus 10 plus 20 plus 2. R type, so 25 plus 5 plus 10 plus 2. Jump is only fetch and decode, so 25 plus 5. I don't know if we have to write these because they don't get executed, right? But I guess I'll see in the answer key. S type, so 25 plus 5 plus 10 plus 20, 25 plus 5 plus 2. Give the total execution time. Do we just add everything up? Like, oh, if he wants a total execution time, we have to add all of these up, don't we? How would, how do we even write that? Does he want us to just like multiply it out every time? Wow, he really does. Okay. So there was, let's do L type and just tally it up. S type, R type, and then there was one jump. Right? Okay. First line is an L type, second is an R type, third one L type, fourth L type is S, L, another R type, one jump, one door, and then one loop. Okay. So it's 5 times 25 plus 5 plus 10 plus 22. 2 times 25 plus 5 plus 10 20. 2 times 25 plus 2 and 1 is 25 plus 5. All right. Yeah. Okay. For the above execution, provide CPI cycles per instruction. Um, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think it's just 10 divided by 10. 10 cycles divided by 10 instructions, which equals 1. Yeah. Oh, it's 10 instructions divided by 10 cycles. So I'm pretty sure it's cycles divided by instructions, but okay. I'm not pretty sure. Okay. Um, for the above execution, provide the count of each instruction type. Okay, well, we already know that. So 5 L, 5, 5 L types, 2 S type, 2 R type, 1 jump, right? Is that what he wants? Yeah. Provide the memory reference string. Okay. So that's going to be 2 here, 2 comma 5 comma 6, or 6 again, 7, and finally 2. 2, 5, oh, 2, 5, 4, 6, 7, 2. Did I screw up? Did I do 2, 5, 6, 4, 6? Okay. This is definitely, there's supposed to be another 6. I think he typoed. 1, 2, 3. Yeah, he just missed one, I think. Do they have an answer key for this one? Direct met. Allocate. That's like way ahead, I think. Yeah, I think it's this one. It's a system with 3 processors. P1, P2, P3 with the initial cache state shown below. Assume if not provided, each data memory location has an initial value of 2 and registers are 1. Determine the state of the change blocks in the caches of all processors after each sequential operation. Okay, so first thing, each data memory location has an initial value of 2, register initialized to value of 1, direct mapping right through allocate. So yeah, right through on right hit, allocate on right miss. Okay. First instruction, L type, right? No, my bad. That's an S type. Right? S type, yeah, because we're taking what's in the register and putting it into main memory. So that's S type. Um, so 3, uh, the cache size is only 2. So 3 mod 2, which is equal to 1. Um, and cache location 1, does it have address 3? It does, but it's invalid, so it's a right miss. Um, allocate on right miss, so we have to read it. Then we check if anyone else has address 3 on their cache. And processor 3 has it. So this one got touched. I think we're in A1. Okay, so this has 3. It's exclusive right now, but because of snipping, it will share it with processor 1. So then this will have a 3. The state is going to go from invalid to shared, but then immediately, um, now that the allocation is done, it's going to write. It's right through. So update the cache and update main memory. Um, so this will become exclusive, and then this one will become invalid after the write because the data just changed. Um, Now, processor 2, address, another S type. So 8 mod 2 is equal to 0. So over here, it does have it. Um, it's exclusive. So when the other processors snoop, nothing's gonna happen, right? Okay, well, it has it and it's a write hit, but it's a write through policy. So update the cache and update the main memory. So address 8 stays the same. It goes from, well, it stays as exclusive. I think nothing else gets changed, so that's fine. Next is a load on processor 3. I'll type 3 mod 2 is equal to 1. We check. It does have address 3, but it's invalid, but that's okay. We're going to change it to, uh, actually, you have to check if any of the other caches have it. So processor 1's cache has it. Um, so when it snoops, it'll drop it onto the bus. So then this will become shared, and also this one will go from exclusive to shared. Um, Another S type. So 4 mod 2 goes to 0. Cache location 0. Does it have it? Yes. Exclusive. Um, Same thing on write. It's a write hit and write to the cache and write to the main memory because it's write through policy. So this will stay exclusive. This will stay the same. Exclusive. Um, Same thing. Valid. 3 shared. Okay, so nothing changed for that one. I'll type for this line on processor 3. 4 mod 2 is 0 again. We check the address. It has it, but it's invalid. Then we have to check if anyone else has it. Processor 1 has it. So this will go from exclusive to shared. And then this will also go from invalid to shared. And then the rest stays the same. Um, okay, so now processor 1 is doing another L type. Um, to cache location 0, but it has it, so that's a read hit. So that's fine. Nothing changes. And then finally, processor 2 is going to write to address 4. So 4 is equal to 0. Does it have it? It does not. Um, so that's a right miss, and that means we have to allocate on right miss. So we have to read it first. So um, we replace address 8 with address 4. Um, then we check if the other caches have it. It does. So this is going to go from exclusive to shared. Um, so right now this is doesn't really matter what shares it, which cache shares it, because both of them have it. One of them will. Doesn't really matter. But then right after that, so now that's allocation done. Um, now it's gonna write. So this will change the exclusive again, but then these will become invalid because it just overwrote whatever was in their caches. It's not up to date anymore. So I think that should be all of it. Let's see if it's right. Yeah, so 3 in exclusive, 3 in invalid. Okay. 08 exclusive. Okay. That's good, I think. And then, yeah, address 1. Oh, sorry, address 3 with shared. That's this line here. Uh, and also shared here. Yeah, shared and shared. Um, and then after that, there's this line. And that is what's changed. 4 is invalid. So nothing changed. It's good. Process 3 R2 goes from exclusive to shared. From invalid to shared. That's right. Uh, for shared, shared, and then last one, invalid 0, exclusive, and invalid. Okay, that's right. These one. Would you mind going over question 3 and 4, where they ask for MAR and DR values once you're done with these, since he hasn't posted answers to those? Yeah, okay. Um, did anyone have any questions for this one before I go back to the other one? Okay. Questions 3 and 4. 1, 2, 3. This one. Okay. Execution cycle. Consider following executable loading to main memory with offset 12. Assume R1 R1 has value 3. R2 has value 2. It's a 64-bit system, so 64 divided by 8 is equal to 8. Assume each data memory location has value of 2, and all other registers have value of 1. Okay. So first instruction, 0, 0, 1, 2, and then you increment by 8 every time. So 0, 0, 2, 0, 0, 0, 2, 8, 0, 0, 3, 6, and 0, 0, 4, 4, and then finally 0, 0, 5, 2. Oh, this is a branch. This is a load. This is an, oh, L type, yeah, L type load, R type, S type, R type. Okay, so value of PC at the end of exec stage. So for branch, there's always fetch, decode, and exec. Um, so in the PC, initially they increment it to 20, but depending on if the calculation from this branch is true or not, it might change the PC. So we have to compare. This is a branch on equal. We're comparing R1 and R2. So R1 is 3, he told us. R2 is 2. So they're not equal, so it won't jump. So the PC can stay at what it was. That's 0, 0, 2, 0. Um, value of the MDR after the exec stage. So fetch, decode, exec, mem, write back. Um, the MDR after the exec stage. So the exec stage is where it sets up the MAR and the control, but it doesn't actually get the data on the MDR until after the mem stage for loads. So it's going to be the MDR after the end of the exec stage is going to be whatever was on it from the previous instruction, I think, right? Or not even the previous instruction, from whatever was there from the fetch stage. So I want to say that this is literally going to have the uh, instruction for this line of code. I'm pretty sure that's what it's going to be because it'll have whatever it got from the fetch stage, which is the actual instruction itself. Value of MAR during write back stage for the next instruction. So our types have fetch, decode, exec, and write back. Um, so for this one, the MAR will have whatever was put into it during the fetch stage because we don't go to main memory for data. So it's just going to have the instruction. address, which means it will go to, this will have 0028 here. S-type, MDR after the end of the stage, fetch, decode, exec, mem. So at the end of the mem stage, it's going to have whatever data we're trying to actually write to main memory. So we have to see if R2 was modified at all, and it was for the second line of code. It was loaded with whatever was in address 3. So that's still just 2, actually, because all addresses by default have 2, he said. So actually it didn't change it. So that's okay. So we'll just put a 2 into the memory address, but we have to convert this from whatever R4 is. I guess it doesn't really matter. We just want to know the data, which is just going to be a 2. Okay. And the last line is another R type, so there's fetch, decode, exec, and write back. Value of z at the end of the fetch stage. So at the fetch stage, the z register hasn't been touched yet for this line of code. So it'll be whatever the z register last had, which would be this R type instruction. So this will just have 2 plus 2, so the z register will have 4. For the above execution, calculate total data memory access count. So we go to get data for the second line of code and the fourth line of code. So that should be only twice. The total memory access count, so that's everything, including instructions and data that we went to main memory for. So all 5 lines of code will run. We went to get data twice, so there should be a 7. For the above execution, provide count of each instruction type for the executed code. Okay, so there's one branch, one L type, one S type, and 2 R types. For the above execution, now assume R1 equals 2 and R2 equals 2, and provide the value of the PC at the end of the exec stage for the first instruction. So this is what I was talking about before. So now, if R1 is 2 and R2 is 2, this is equal. So this branch will be true. So we have to update the PC to whatever the instruction count, sorry, whatever the program counter is for that line of code for X. X is down here, which is 44. So it's going to be 44 here. So 0, 0. Oh, wait. It says after the end of the exec stage, though. Fetch, decode, exec. Yeah, okay, after the exec stage. Yeah, so it'll update the PC to 44. For the above execution, now assume R1 is equal to R2, provide CPI. Um, okay, so if it did jump to that one, line 2, line 3, and line 4 won't run if the branch is equal. So it's only this one and this one. So it should be 2 divided by 2, which equals 1. There's no way to know if our answers are right, but I'm pretty sure this is right. Okay. Next question. Question 4. Assume the program is loaded with offset 25, 16-bit architecture. 16 divided by 8 is equal to 2. Each data memory location has value 5. Every register has a value of 4. So the first line of code is 0025, increment by 2 every time. So 0027, 0029, 0031, oops, 0033, 0035, 0037. Okay. Provide the value for PC during decode stage of instruction 5. So actually, maybe I should just write down what these all are. This is an R type. This is an L type. S type, R type, R type, R type, branch. Um, so the PC during the decode stage of instruction 5, it's going to have already incremented the PC counter. So it'll be 0035 because it will have incremented it to the next line. Provide the value for MAR at the end of write back stage for instruction 6. An R type instruction, so there's fetch, decode, exec, write back. At the end of the write back, what is the value in MAR? Well, memory wasn't touched because it's an R type instruction for data. So it's going to have the instruction still, the instruction address. So that will be 0035 also. Provide value of for MDR at the end of exec stage for instruction 3. It's an S type instruction, so it's fetch, decode, exec, mem. Provide value for MDR at the end of the exec stage for instructions 3. So at the exec stage, it's going to set up all the registers for that. Since it's a S type instruction we're writing, the data will be put in the MDR. So we're putting whatever's in R2. And R2 has a 25 from the first line of code. So MDR will have 25. Provide the value for the Z register at the end of exec stage for instruction 4. Okay. That's an R type. So fetch, decode, exec, write back. So during the exec stage is when the LU is going to be used. So instruction 4, R2 plus R3. So R2 has 25 plus whatever's in R3. R3 we loaded at address 55. Um, all the addresses are initialized to 5. That's going to have 5. So 25 plus 5. So the Z register will have a 30. Um, total memory reference count when the above looped instructions are executed. Okay, so 9.3 is where the branch jumps to. Compare R5 and 3. R5, R5 literally gets a 3 into it. They are equal. uh, Since they are equal, it's not going to go back to the Y label. So everything only runs once. So there's 7 lines of code, so that's 7 memory accesses for the instructions. And then there's 1 L type, 1 S type. So that's plus 2. So 7 plus 2. So that's 9. Provide total data memory reference count. That's 2 because we go to main memory for data for that 1 L type instruction on line 2 and 1 S type instruction on line 3. Provide the memory reference string for the above looped execution. 55, 5. Okay. Any questions? Um, we'll go to this one. Oh, I think we did this yesterday. No, did we not? 2, 3, 6, 5, 3. Oh, I did the OPT one. Okay. 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 So I can do this one. All right, we'll do least recently used. Okay. Um, 0, 1, 2, 3, 2, 3, 6, 5, 3, 3, 5, 6, 2, 4, 5, 6, 7. So it's fully associative. So that's just fill in whatever you can and then replace it with LRU. So 2, 3, 6, 5. 3 is going to be a hit. So I'm going to move, I'm going to keep track of it here. So 2, oops, 2, 3, 5. And then 3 is a hit, but then we have to move it to the front. So now it's 2, 6, 5, 3. 4 is a miss. So now we take out 2 because that was the least recently used one and replace it with a 4. So 6, 5, 3, and 4. We replace the 2 with a 4. 5 is a hit, but now we have to move 5 to the front. 6, 3, 4, and 5. 3 is a hit. Same thing. Move it to the front. 6, 4, 5, 3. 5 is a hit. So move 5 to the front. 6, 4, 3, 5. 6 is a hit. Move that to the front. 4, 3, 5, and 6. 2 is a miss. So take out 4. Put 2 in the front. And then 2 replaces whatever 4 was. With that. Now 4 is going to be a miss. So replace 3. So 5, 6, 2, and 4. 4 will go here. 5 is a hit, so move this to the front. 6, 2, 4, 5. 6 is a hit. I'm just going to put on the right side. So, 2, oops, 2, 4, 5, 6. 7 is a miss. So 7 replaces wherever 2 was. That's there. And then 4, 5, 6, 7. 5 is a hit. So move this to the front. 4, 6, 7, 5. 1 is a miss. So replace 4 wherever 4 was. So put 1 there. 6, 7, 5, 1. 4 is a miss. Replace wherever 6 was. All the way out here. So 4 goes here. 7, 5, 1, 4. And then 5 is a hit. So 7, 1, 4. Okay. So we had, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 hits. It looks like. And misses. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 misses. Did I got that right? Yeah. 9 total hits, 10 misses. Okay. I think that's right too. 2, 3, 6, 4, and then put a 2 there, put a 4 there, 7, 1, and 4. Yeah. Okay. I think this way, just doing it this way, the way I did it yesterday was kind of confusing and clean. I think you should just make the new a new line every time. And that's for the memory. Okay. Oh, he didn't ask for that. The following executing program. Which question is this? This one. For the following program executing on a system with the direct mapped cache of size 2, initially empty. Okay, so direct right through on right miss. You didn't say what happens on a. Oh, sorry. Oops. Right through on right hit, and then allocate on right miss. So right through on right hit, allocate on right miss. For each data memory access, classify the types of cache misses. Also provide the total memory access time, where main memory access time is 30 nanoseconds, cache access time is 2 nanoseconds. If not provided, assume each register has an initial value of 2. Okay, every register has a value of 2. Every memory address has an initial value of 5. Okay. Oh, this is gonna be gross. Okay, so this is going to be an S type. L load store load store load. Okay, so definitely the first line of code, if the cache is empty, this is going to be a compulsory miss. We're going to allocate on right miss. So, thank God there's not multiprocessing, but that means that 2. Map cache of size 2. Am I missing something? Why are there more rows than I need? Okay, well, 2 mod 2 is equal to, yeah, alright, well, okay. So 2 mod 2 is equal to 0, so the 2 goes here. L type instruction is going to be a compulsory miss, not in the cache. So this is 3 mod 2. Three is going to go here. 6 mod 2 equal to 0. So 6 goes here. 6 is going to go here. So this is a compulsory miss, but it's also a conflict miss, but it's also a capacity miss. My God. 5 mod 2 equal to 1, not in the cache. allocate, so 5 places here. Same thing. Compulsory, conflict, capacity. 3 mod 2 equal to 1. Thing A, B, C. This row gets replaced with a 3. 4 mod 2 equal to 0. Again, compulsory, conflict, and capacity. Five mod 2. Miss again, allocate. 5 was here. 3 mod 2 to 1. Same thing. 3, 3. 5 mod 2 to 1. Everything. 6 mod 2 equal to 0. This better be the right answer. Um, we missed every single time, it looks like. Total data memory access time. Okay, so for every write miss, there's also an allocation, which is a read, which is another time you have to access data. So every time there's a write miss, it's actually twice. So there's a miss every time. So once, twice, 3, 4. So it's 4 times. What's the formula? To bring up the It's H times TC. This is not enough space for it. H times TC plus M times M plus P. Okay, so there was 0 hits. So 0 time for accessing the cache. Cache access time is 2 nanoseconds. Well, it doesn't really matter, but 0 times 2 plus how many misses were there? There was definitely 10 misses for all of these, but then for the S type, there's 4 more. 1, 2, 3, 4. So it's 14. 14 misses times memory access time is 30. Did he say a penalty? Memory access time is 30. Cache access time is 2 nanoseconds. So I guess there's no penalty. 30 plus 0. I hope this is right and I didn't totally just like bullshit everything. Oh, whoops. Okay, no, I had it right initially. The first two are just A and A, and then everything else is A, B, C. Mm, oh, what the fuck? Mm, 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 mm. Okay, so did I do it right? I technically did do it right. He just wrote the formula differently. Because every time there was a right miss, he wrote 60. Um, he did it like this, but it's the same as this because this is actually 8 times, sorry, this is 8 times 30. It's the same thing. So 8 plus 6 is 14. Yeah, it's the same idea basically where that when you have a right miss and it's allocate, you have to go to main memory twice. Um, that's everything that we have answers for. Um, it's also 11 o'clock, so maybe we should just wait unless someone wants to do something else. Um, okay, if no one has any questions, oh, okay. Um, okay, I guess if no one has any questions, then we can end it here. And then if he provides the answer key for the rest of the questions, we can go over it. I'll just stop the recording.